In reading this section, I hope that by the time we're at the end of this handout that you can read it a little bit easier so that you can follow the steps and follow the reasoning behind the ideas, how to solve the least squares problem, and also some of the motivations for how much simpler that problem becomes in the case of A equals QR. So following those steps, I want to highlight just some of them here. So remember, at the beginning of the handout, which would have been days ago by the time you're at this point in the handout, we talked about the projection matrix into this direction x hat. There's this formula that's all over the textbook and on the handout, but then there's also this formula, which is nicer, and they both give the same thing. Compare that to what we have up here. This comes from the normal equations, and look at all the things we have to do to the matrix A to get this projection matrix. Look how also this compares to this down here. In the case of down here, x transpose x is a scalar. We can actually divide by a scalar. Up here, A transpose A is still a matrix, so we can't divide. So we have the inverse up there. But look, it's the A transpose, and then it's the inverse of A transpose A, just like we have down here. So that's fascinating. But look how it simplifies if you do that factorization, A equals QR. If you plug QR in for A everywhere here, the steps are shown on the handout, and you should be able to work through those steps to show how this simplifies to just Q transpose in the same way that this can simplify to x hat transpose. So an orthonormal basis makes the least squares problem much nicer to solve, just like normalizing vectors made projection matrices much easier to represent. So this ends the theory section of this handout. There are a few applications left to go.